Welcome everyone to GeoHug. So I'm just promoting you as panelists. Please don't be shy. Come on through, get the cameras on, get the mics on. We've got the lovely Nicole Januszczak with us today. So yeah, make sure you come on through and you'll have the chance to chat with her directly at the end. But before we do start today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, this is going to be an awesome one. I'm very happy that we have Nicole Januszczak with us today. So Nicole is the practice lead predictive capability for BHP's exploration group, and with the aim to be disruptive in extracting value from data and applying mineral systems to enable a step change in the discovery of world-class resources. And today it is going to be brilliant as she shares how BHP are preparing to use AI at scale and at pace to accelerate the delivery of high value options to the business. So it's going to be a fantastic session. I hope you all enjoy it. And yes, thank you so much, Nicole, for joining us today. It's awesome having you here.
Great to be here. Thanks so much, Jess.
So before we do get stuck into your presentation, I was wondering what got you into geology to begin with.
It was an undergraduate field trip to the Canadian Rocky Mountains when I was an undergraduate. I didn't have any of the prerequisites, but I loved being outdoors and in extreme remote places. And honestly, I learned more in those 2 weeks in the field than in an entire semester in the lab. So by the time I got back, I was absolutely hooked.
I love that. And what have been some of the favorite places that you have seen?
Oh my goodness. I've been so fortunate. One of my favorite summers was spending the summer up in the Arctic on a field season, uh, you know, daylight 24 hours, and then spending that same winter on a ship in Antarctica,
Oh, wow.
daylight 24 hours. So, needless to say, I got a lot of vitamin D that year.
Wow. Is that boat trip as crazy as everyone says?
It was pretty epic. We had to sail um, from Tai. Where did we sail from? We sailed from Fremantle, actually,
Oh,
down to Prids Bay and then back to Tasmania. And those roaring 40s as you go south are as epic as they say they are. We literally had to hold on to the couch in some weather.
oh my gosh, that's incredible. What an experience. And did you bring any pet rocks along to show us today?
As luck would have it, I brought this little number, Jess. Where's my camera? I just happen to have a very small pet rock, and this is an eclogitic mantle xenolith. It sits on
Ooh.
my dining table, and I happen to have a lot of geos around that table. And I actually wait and see who comments on my mantle xenolith sitting on my table. I've
That
spent a lot of my time in my career thinking about what's happening hundreds of kilometers below our feet and how that helps drive our mineral systems. We're looking for those crazy scenarios where a very behaving geological system goes absolutely rogue. It throws itself into disequilibrium under transient conditions and enables this world class mineralization to form. So I love having this long traveled token to remind me on my dining table, these remnants of a subducted oceanic slab preserved deep in the lithospheric mantle. I mean, how cool is that? We really have the most amazing jobs in the world.
you really do. I have a whole new appreciation for what you all do now since doing all of this. So it's so epic. But yeah, thank you so much for joining us. It's absolutely brilliant having you here today. Yeah, if you want to share your screen and can get stuck into it. I'm looking forward to it.
It is such an honor to be presenting on GeoHug and amongst the incredible lineup that you've had this month for coffee, Isra and Anna and Antoine. And I want to thank you, Jess, and you, Kathy, for all the hard work you do pulling our community together. You're such incredible role models for both seasoned folks like myself and early career geoscientists alike. So I'll start with all the things that I'm not saying in my presentation today. So first off, I'm not saying that I'm an AI expert. There are much more knowledgeable people listening today, but like all critical disciplines in exploration like geochemistry or geophysics, I've needed to educate myself on AI as another critical tool in our arsenal to predict world-class mineral systems, which of course is where we find those world-class deposits and mines. So I'm sharing my thoughts on how we can harness AI to help us predict the next giant mineral deposit. I'm also not saying that BHP is on the bleeding edge. On many parts of our digital journey, we're actually trying to catch up, but I think that we're doing some really cool things that I'm excited to share with you all. And there are many companies out there doing amazing things in this space. And of course, I'm not saying that AI is our silver bullet. I'm a geoscientist who still gets excited by mylar and a stereoscopic pair of air photos. So for me, this is all about leveraging the best of both worlds, world-class geoscience and emerging AI tech, so we can provide the world with the raw materials that it needs for us to live here in a sustainable way now and for the generations to come. So our standard company disclaimer before I move on. And just because it's GeoHug, I thought I'd start with a few words about my air fryer. So early air fryers, the first one I got, it was crazy expensive and it had this itty bitty real estate in the pan. The one that I had was not nearly as fancy as the one you see in the photo here. It was heavy. It took up a huge amount of my counter space. I actually hated it. I didn't really know how to use it or why I had it, so it sat idle. And then I started making chicken fingers for my son. I could only do about half a dozen or so at a time, which drove me nuts, but he loved them. So I kept making them. And then something happened. I saw a recipe somewhere, or I started warming things up in it. Started roasting stuff and baking and even dehydrating. Wow, the possibilities were endless. And then it broke. And I was honestly so sad. But then I went out and I bought a bigger one and a better one for less than half the cost of my original. And now I use it almost every single day. And I've even convinced a friend of mine to buy one, and they're loving it too. But some people don't have air fryers yet, or some have one, but they don't know what all the hype's about. Some have tried it, but they don't use it routinely, or they use it for simple basic tasks like chicken fingers. Those who are using it see the value of preheating more quickly, cooking food faster, plus the less obvious benefits of using less energy and keeping the house cooler, for example, in the summer, like we're experiencing here in North America. So perhaps a tiny bit of a stretch, but just like with my air fryer, many people are at different phases of their AI journey. The article on the left from The Economist says that beyond America's West Coast, there's actually little sign of AI having much of an effect on anything. On paper, we're told that AI will transform the global economy, and we're watching company valuations go through the roof. But for AI to fulfill its potential, firms have to buy the tech, shape it to their needs, and become more productive as a result. One of the big problems is the rate of adoption. Companies are putting out startling estimates of how many people are using AI, and a recent report by Microsoft and LinkedIn says that 75% of global knowledge workers, those of us who sit in front of a computer all day, use it. So people, by all accounts, are in an AI world, and in a sense, we are. Every time we do a Google search or pick a song on Spotify, we're using AI. But the incorporation of AI into business processes remains a niche pursuit. AI will reward early adopters, but the challenge for businesses like ours is how and where we apply it. At the same time, concerns about data security, biased algorithms, and hallucinations are widely shared. And some groups might be stuck with pilotitis, where too many small AI projects are making it really hard to identify where the value sits and where to invest. And others are waiting simply because the tech is developing so fast, they don't want to invest in something that's soon going to be out of date. So thanks for permitting me my rant about kitchen appliances. Today, we're going to discuss how we as an industry are struggling to deliver the raw materials that the world needs at pace, how we harness the power of the AI tidal wave, where on earth do the geoscientists and the mineral systems fit in, and a bit about what we're doing about it at BHP. So mineral exploration suffers from a prediction problem. We're good at predicting mineralization, but not very good at predicting world-class mineral systems. And this is essential because this is where we find those world-class deposits and mines. So this is a plot of the discovery history for porphyry copper deposits showing cumulative contained copper on the y-axis and time along the x-axis. And the gray curve shows all copper resources that have been discovered. And all of those deposits that have become mines are shown with the black triangles. We've split out all of the relatively large resources, those greater than 5 million tons and greater than 0.5% copper equivalent, with those projects sitting in pre-feasibility in red, sitting undeveloped in cyan. And those larger resources that have become mines are shown with the green triangles. And this plot highlights eras of discovery based on disruptive technology like bulk mining, airborne geophysics, stream sediment geochemistry, and the adoption of the porphyry deposit model. As an industry, we've evolved from one that was largely observational to one driven by physical properties and then model driven. And we see there's a major upsurge in discovery after 1955, largely enabled through detection using geophysics. But the proportion of discoveries converting to mines starts to diverge strongly at about the same time. You see those gray and black curves progressively moving further apart. And when we look at larger material mines, the quality gap is even more striking. And after 1980 and the discovery of Escondida, the significant uptick in the curve there, the mine curves flatten out significantly. So in other words, we're finding mineralization, but not finding new mineable resources. And we need to figure out a way to disrupt this quality gap. So at BHP, we use prospectivity maps to predict where we should be exploring, and these maps are rooted in mineral systems. So we use mappable proxies for those critical processes that we think need to line up in space and time for a mineral system to form. We've created repeatable workflows designed to use all of the available data regardless of the sparsity of the coverage, which is important because sparse data coverage often represents an opportunity. And we estimate and propagate data confidence. So that's all good. On the left, I'm showing an example of mineral system elements observed in regional data for porphyry deposits. And in this case, we're looking at fertility. And fertility in the porphyry copper context equates to the propensity of a magma source to produce ore-forming magmas, and the controls are a range of dynamic mechanisms that keep arc magmas pooled at the base of the crust for extended periods. A number of proxies exist that map this condition. We can use lithogeochemical trace element data, like you can see on the left at the top, and we can use geological and geophysical evidence and plate models to inform us about the prevailing stress regime, the subducting plate topography, crustal thickness, and the geometry of the subducting environment. The resulting prospectivity outputs govern critically important exploration decisions, where we play on our level of investment. On the negative side, these models take us months to build. Our geoscientists are under considerable cognitive load and can only extract a fraction of the available knowledge and information sitting in data and reports. The outputs are semi-quantitative and static. They incorporate only a limited number of variables, and we use too few techniques to stress test our understanding of how the critical processes need to line up for these world-class systems to form. So the resultant maps are often overly permissive and low confidence. But if prediction is the key to discovery success, how can we get better at it? To highlight why we need to get better at prediction, I'm going to borrow from a recent LinkedIn post and publication by Adam Simon at the University of Michigan. The plot on the left shows that copper deposits at depth, and those even more than 1,000 meters below, of course, can be economic. And Adam asks, what truly breakthrough exploration strategies are being used to discover buried deposits? In his 2022 paper, Friedrich Wellmer says that exploration discoveries show episodic behavior, and so far, all pessimistic forecasts have been proven wrong by ingenious advances to detect new ore bodies. I believe that this is the type of breakthrough that Adam's referring to. We've seen and heard a lot about the future increased demand for copper, and a recent paper by Lawrence Cathels and Adam Simon for the International Energy Forum puts this in the context of the copper required for electric vehicles. EVs require substantially more copper than other metals than internal combustion engines. So the figure on the right looks at mine production required between 2010 and 2060. And the solid black baseline curve represents mining needed to satisfy S&P Global's projected non-transition copper demand. So the increase just allows for the developing world to catch up with the developed one. The gap between the orange hybrid curve and the black baseline is the amount of additional copper that must be mined to manufacture 100% hybrid vehicles rather than internal combustion. And the gap between the dark blue EV curve and the baseline is the mined copper needed to manufacture 100% EVs. The light blue curve shows the additional copper needed to upgrade the grid to support all of those EVs. And then, of course, that green curve and the gap between that and the baseline is the copper that wind and solar will need to fully replace fossil fuels by 2050. The team put this into context further by calculating the number of El Teniente mines that have to be put into production each year to satisfy the demand in each scenario. And they chose Chile's El Teniente because it produces at a rate that equals the average production of the top 10 currently producing copper mines. So staying on that business as usual baseline requires that we put 1.1 El Teniente mines into production each year for the next 32 years. To reach that 100% hybrid manufacture requires 1.2 L tenientes per year. 100% EV manufacture requires 1.7 L teniente mines per year. And replacing fossil fuels by wind and solar by 2050 requires us to put into production 6 El Teniente copper mines per year. Soares from S&P Global examined the development pipeline, including mine closures of our current resources. And you can see his brown dashed line curves on this graph that show the number of potential mines in the pipeline won't meet even business as usual baseline needs after 2030. So the demand requires true breakthrough exploration strategies. The good news is that we have new technology with this tidal wave of AI heading our way. AI will reward adopters. However, the challenge for exploration is how and where to apply it. To do this, we need to understand what it is and what it isn't. And to do that, we're going to walk through a few myths out there regarding AI. I'm going to borrow from a number of different sources as I walk through this, but impactful for me was a keynote on machine intelligence at the Creative Destructive Lab Super Session held last month in Toronto, where Sendil Mullainathan used this quote: "Of all things happening in machine intelligence, the biggest impact will be in science. Like the invention of the microscope, we will see things we have never seen before." So the first myth is that Gen AI are robust to many applications. In other words, if it can do this, then it must be able to do that. And this is not necessarily true. If a large language model can predict the next word in a sentence, we assume that it understands the world from the text that it has looked at. Algorithms can do well without having the right world model, so it can get the right answer for the wrong reason. If you add a detour, it can go haywire. So it works really well on specific tasks, but gets a little brittle when you try to expand it out too far. This article is from the New York Times in 2018, when large language models were just coming to light. OpenAI and Google's BERT had analyzed thousands of books and Wikipedia to learn a particular skill by analyzing all of that text. OpenAI's tech wanted to guess the next word in a sentence, and BERT wanted to guess missing words anywhere in a sentence. And in mastering these tasks, they learned many of the fundamental relationships between words in the English language. And this was a real wake-up call for AI researchers at the time, because they had assumed that language technology had hit a ceiling. So this type of machine learning using complex mathematical systems, or neural networks, also sometimes referred to as deep learning, was possible because of the enormous amounts of processing power that was now available to neural networks. BERT analyzed all of that content over the course of a couple days using dozens of computer processors built specifically for this task by Google. The idea had been around for years, but the hardware had to catch up. And now, of course, we have quantum computing just around the corner. So for mineral exploration, we need to define specific tasks for AI and resist the urge to apply it randomly. Well, if it can do this, it must be able to do that. There is no one size fits all solution with respect to AI. And experience from other industries help, but there are always important specificities to industry knowledge, the type of the large language model that we use, and the source data sets that we use as well. Manual testing is important, and business subject matter expertise oversight is required. Critically, AI can assimilate enormous volumes of data really quickly and provide summaries and insights. And humans, of course, we can ingest only a limited amount of data and extract only a small fraction of the available knowledge sitting in that data. So in this way, AI can help relieve our cognitive overload and help us discover new insights. The second myth is that AI is there for simple, repetitive, low-stakes tasks. The first wave of AI really focused on let's train it and let's automate it. Let's have AI take care of those mundane, repetitive grunt work tasks, or even better, have AI make things safer and more productive. And at BHP, we're very proud of our progress with driverless technology, for example. South Flank West Australia iron ore achieved 100% autonomous haulage in June 2023, and our Spence mine in Chile achieved this same milestone in April of this year. And BHP also unveiled the world's first automated ship loaders back in June 2022. But the next wave of AI will focus on prediction, and this is where AI can have a huge impact. So as an example, we're going to look at judges. Predicting the likelihood of someone reoffending in pre-trial decisions of who waits for their trial in jail and who gets released on bail or conditions. So this decision can reduce costs by foregoing unneeded incarceration, and it can greatly improve the lives of those who are charged and those potential future victims of reoffenses through better prediction. So this is an example of a really complex decision, and this is what judges go to school and train for. Judges go to law school, they have careers as lawyers before they reach the bench. Algorithms look at the data in front of them and they form a prediction. And in this study, an algorithm produced a pretrial misconduct risk score and release recommendation based on the data it saw. So judges had access to those outcomes, the information that the algorithm looked at, and they also had some other information like the details of the current charges and the demographics. The judges overturned 66% of the algorithm's recommendations, and notably 54% for those that it deemed high risk. So the judges jailed more broadly and evenly across all risk categories. They jailed more people who were lower risk and released more that were higher risk. And on average, the judges underperformed the algorithm. And there was some important heterogeneity across the judges as well. The graph on the right shows that if prior to a pretrial release hearing, a low performing judge heard a case involving an unrelated defendant who was arrested for a serious felony while on a pretrial release, the judge's release rate for other defendants declined in subsequent weeks. So lower performing judges placed a much greater importance on demographic factors like race, while higher performing judges focused on factors not considered by the algorithm, like substance abuse or the ability to pay bail, attaching non-monetary conditions around bail, for example. So the researchers concluded that the use of additional information not considered by the algorithm can make it possible for a skilled human and an algorithm working together to outperform either the algorithm or the human alone. So for mineral exploration, we need to understand and accept that AI will help improve our predictive capabilities, no matter how much schooling or experience we may have. We all come from different backgrounds that are impacted by extraneous events in different ways, and an algorithm and a human outperforms either on their own. The third myth is that AI is incomprehensible. We've heard the phrase black box a lot, and these refer to AI systems with internal workings that are invisible to the users. You can feed them an input and get an output, but you can't examine the code or the logic that produced the output. And there are three components to machine learning: an algorithm or set of algorithms, training data, and a model. The algorithm is the set of procedures, and in machine learning, an algorithm learns to identify patterns after being trained on a large set of examples, the training data. And once a machine learning algorithm has been trained, the result is the machine learning model, and the model is what we use. Any of these three components can be hidden in a black box. If the algorithm is publicly known, for example, to protect IP, developers will often put the model in a black box so they can obscure the data used to train the model. An AI glass box is a system where the algorithm's training and model are all available for anyone to see. But believe it or not, researchers sometimes even characterize these as black boxes because they don't fully understand how machine learning algorithms, and particularly deep learning ones, operate. And there's a lot of good reasons to be wary of these. Suppose a machine learning model has made a diagnosis about your health, or has helped your doctor prescribe your course of treatment, or has determined whether you qualify for a loan from the bank. You're going to want to understand how it came to its recommendation. So the field of explainable AI is working to develop algorithms that, while not necessarily glass box, can be much better understood by humans. So this paper from March 2023 begins with a really striking fact. When a deep learning model was built to predict whether a judge will detain or release a given defendant, one single factor emerged as having the largest explanatory power, and it was the defendant's face. A predictor that looked at only the pixels in the defendant's mugshot explained 1/4 to nearly 1/2 of the predictable variation in detention. Defendants whose mugshots fall in the bottom quartile of predicted detection are 20 percentage points more likely to be jailed. By comparison, the difference in detention rates for those arrested for violent versus non-violent crimes is less than 5 percentage points. So on the top panel on the right, we see the face of a white Hispanic male defendant using a morphing procedure to increase the predicted detention risk from 0.41 on the left and reducing the predicted detention risk down to 0.13 at the right. And a generative adversarial network, or GAN, was used to produce synthetically created faces of those more or less likely to be retained. And a GAN is a class of machine learning, deep learning, that trains two neural networks against each other. They compete to generate more authentic new data from a given training data set. The panel in the middle shows the different intermediate images between those two endpoints, while the panel at the bottom shows the predicted detention risks for each of the images in the middle panel. So what's the difference? What are the judges basing their decision on and didn't even realize? What is it about the face? We don't speak the same language as an algorithm, but we both know what a mugshot looks like. The algorithm has found something that we didn't know, and it's communicating it back to us. So what's more important than violent crime or murder? Apparently, being well groomed or having a fuller face gives you a higher probability of being released. So, for mineral exploration, AI can create synthetic data to help us understand its predictions and explain its insights. Simulating and modeling with synthetic data can help us test possible scenarios with quantitative outcomes. Human prediction is relatively simple. We consider tens of variables versus the hundreds of variables that a complex AI model can use to predict. And as shown by the judges, the human model often puts the wrong weight on certain variables. The last myth I'm going to discuss is that AI is more biased than we are. Human conscious and unconscious bias are well documented, and society has been wrestling with how much human bias is making its way into our AI systems. In 1988, the UK Commission for Racial Equality found a British medical school guilty of discrimination because the computer programming it was using to determine which applicants would be invited for interviews was biased against women and those with non-European names. The program, however, had been developed to match human admission decisions, and it did so with 90 to 95% accuracy. Over 35 years later, algorithms are increasingly more complex, but we face the same challenge. Bias can creep into algorithms using training data that includes biased human decisions or reflects historical or social inequalities, even if gender, race, or sexual orientation are removed. Amazon stopped using a hiring algorithm after finding that it favored applicants based on words like executed or captured, which were more commonly found on men's resumes, for example. And another important source of bias is flawed data sampling, in which groups are over or underrepresented in the training data. So, for example, facial analysis technologies have much higher error rates for minorities and minority women in particular because they're not well represented in the training data. On the plus side, machine learning systems disregard variables that do not accurately predict outcomes in the data presented to them. This is in contrast to humans who may lie about or not even realize the factors that led them to hire or disregard particular job candidates. It's also easier to probe algorithms for bias, potentially revealing human biases like the judges that have gone unnoticed or unproven. And you could really argue that the human brain is in fact the ultimate black box. So for mineral exploration, algorithmic bias is a big risk. Uncovering bias in humans is hard. I can't just ask someone else what their biases are, but you can ask an algorithm, if I do this, what will you do? Uncovering bias is theoretically easier. Fixing bias in humans, well, after 20 years of unconscious bias training, we can all have a discussion about how much further we're along. But in algorithms, you can find bias in the code, you can fix it, and you can implement change. We do have a serious sample data issue. Our extraordinary world-class mineral systems are anomalous and therefore underrepresented in training data. So errors and inaccuracies remain a big concern for prediction and exploration. So that's great, Nicole. This is a GeoHug talk, and so far you've gone from air fryers to judges. So what does that mean for me? How do we practically apply AI in mineral exploration? So the opportunity here is enormous. So we've learned that AI can assimilate large volumes of data and extract knowledge. So think about the proliferation of pre-competitive data, press releases, 43101s, research publications, JORC reports, not to mention our own internal data. New insights will unlock new connections in a mineral systems context. AI are better at making complex decisions. This will help improve the quality of our predictive models and help us zero in on those key technical risks that need to be addressed in our work programs. And AI can communicate their logic back to us when sharing something that it has discovered that no one else has known before. This is true insight discovery. And this will help reveal the different combinations of critical elements that are capable of producing world class systems in different scenarios. And machines will outperform us in tackling bias, including that they will operate and learn across scale, incorporating learnings from prospect scale work to impact predictions at much larger scales. So prediction is where we want to apply AI. If we look for those problems and decisions that rely on prediction and where we know we can do better, our biggest decision is where we want to be on the globe. What basin, belt, or arc has the potential to host a substantial mineral system, and then where within that district a number of deposits could be clustered. If we make that decision wrong, it doesn't matter if we're the best explorers, the world-class deposit won't be there to be found. And we geoscientists have a huge role to play. When American planes came back from engagements over Europe in World War II, they were covered with bullet holes in the fuselage. And the officers saw a great opportunity to get more protection with less armor by concentrating the armor where the planes were getting hit the most. So they asked mathematician Abraham Wald to tell them exactly how much more armor they should put on these parts of the plane. And Wald said that the extra armor should actually go where the bullets aren't, on the engines. And Wald's insight was simply to ask, where are the missing bullet holes? And the missing bullet holes were on the missing planes, those that had been shot down. So the reason planes weren't coming back with fewer hits to the engine is that the planes that got hit in the engine just weren't coming back at all. So machine learning takes empirical observation and pattern detection to the next level in multivariate, multidimensional space. But what's the story behind the data? We have to seek to understand what those patterns represent and those underlying processes, or we risk chasing a lot of false positives in our exploration programs, or worse, exploring in the wrong areas. Right now, we train our algorithms using occurrences at or near surface. Does that help us or hinder us when looking to predict deposits under cover? Like the fighter planes from World War II is our training data set introducing survivorship, or in our case, near surface bias. Explorers naturally divide into two camps: those that are more data driven and like to follow empirical patterns in the data to lead them to the next opportunity. And then there are those that are more conceptually driven. This is how we understand a given mineral system has formed, and therefore these are the elements we're going to look for as evidence that the processes were present, effective, and all happened in the right order. And the reality is that we really need both. They're complementary. Empirical exploration shows you emergent patterns in big data sets, showing you correlations that should make your conceptual half of your brain go, what's the underlying process here? And we, the geoscientists, are the ones that have to ask these critical questions. The unknown is far larger than the known, and we wrangle with the known in our minds every day. With AI's help, we can look at patterns in the unknown. Algorithms will look at the data, notice things we can't, and then communicate them back to us. This insight discovery will really help improve our predictions. The rate limiting step so far has been reliance on our human intuition, and that's about to be unlocked. The Economist article on the right tells the story of Geoffrey Tandy, who was recruited by the British government to work at the Allied Troops Code Cracking Center at Bletchley Park. Now, Tandy was a cryptogram expert. That's an expert in the study of algae, not a cryptogram expert, which is an expert in encrypted text. And the story may be a bit apocryphal that he was, hired on someone who missed a letter in a word. But Geoffrey Tandy's botanical knowledge helped crack code, and his expertise on saltwater algae proved essential in recovering German codebooks from the sea. But it's fair to say that he wouldn't have made it through the recruitment process of a modern high performing company. But it does sum up the combination of random skills, dedication, people who think in different ways, leading to spectacular innovation and sustained success. And in this example, in the war effort. And the image here is just a cartoon representing Billy Knox, who was a professional papyrologist who apparently installed a bathtub in the Admiralty office during World War II and apparently cracked a German cipher code during a soak. So working with AI to improve our predictive models is going to require people who think in different, original, and unusual ways. And the point may not just be what you know, but more how you think. So AI is a really powerful tool to improve decisions that rely on prediction, but the first step is really to build the foundational data sets required to support it. Now, BHP exploration has been around for over 100 years, and our footprint has expanded and contracted multiple times over that period. And for the last few years, exploration's been expanding from essentially a single commodity on a single continent to a truly global team that spans 5 continents. Our data solution is trying to keep pace as we move from file servers based in Santiago to a single source of truth, centralized cloud based infrastructure with working domains in place to support our global operating sites and contains standardized data that our geoscientists can easily access. So the idea is to address issues of data quality, consistency, and access, being able to find your data interoperability, so removing the need to transfer data between tools, removing a lot of manual rework and the complex data pipelines that we had in place, and then making sure we have data lineage for those secondary products, those models, those interpreted products, that they retain their vital context. First and foremost, critically, this puts our data at the fingertips of our geoscientists, but it also means that our data is ready for data-driven applications using machine learning and AI. So the hardest part of exploration really shouldn't be looking for our own data, and so we've been investing a lot to get it right. At BHP, we're curating one of the largest cloud-hosted data lakes in the world as a key enabler for the advanced application of AI. We're using the Open Subsurface Data Universe, or OSDU, to help us address those key challenges of data silos, data standardization, interoperability, and data lineage. We're doing this in exploration, and we're hoping to see it cascade across BHP as a whole, because if we get this right, we will effectively pull the value of every single piece of data that we collect across the entire value chain at BHP. Beyond BHP, we envision a data ecosystem whose foundation is an open source cloud based platform like the OSDU for the mining industry as a whole, where governments and research partners can share data, codes, and workflows. And in this way, we could collectively lower the bar to entry and enable access to standardized data and workflows to industry players, both big and small. We don't compete in how we structure data. Standardized data schemas are already being shared. We also don't compete with pre-competitive or research data. And we can define APIs or application programming interfaces to access the data platform so anyone can develop apps in the OSDU and elect to make them open source or not. And many of us have experience with open machine learning codes or open geophysical inversion codes that have improved dramatically and really quickly thanks to these being made open source and available. We're investing in new spatial temporal data sets that are revealing how world-class mineral systems form, many of which are built or interrogated using machine learning algorithms. One example is our Stellar project with the Earthbite Group at the University of Sydney, where we're modeling the extremely dynamic nature of the Earth with plate models, mantle models, and Earth landscape evolution models for the last billion years. We're building in-house AI toolboxes and rolling out a data science capability program, providing machine learning training to our geoscientists. Our toolboxes put new tools into the hands of our geoscientists, and they've relieved significant bottlenecks in our predictive modeling workflows. Our geochemical toolbox is a great example. It provides advanced analytical tools to perform the data cleaning, the imputation, but also critically multivariate analyses in machine learning for geochemists to process, analyze, classify, and interpret our data in a robust way and in a spatial context. These tools are really user-friendly and can be applied to projects from anywhere across the globe. And we're pioneering the use of large language models in BHP to extract mineral system insights stranded in our unstructured legacy data. We're using a chatbot pointed at an internal trusted data source, and in this case, using, again, retrieval augmented generation, or RAG, to optimize the outputs of a large language model, referencing one of our own trusted internal data sources. In this way, the RAG extends the already existing powerful capabilities of a large language model to our internal knowledge base, all without the need to retrain the large language model. The RAG will only use the information provided in the data source to generate its answer, so it won't refer to the base training set. And it has the ability to provide references or sources that it used to generate the answer. So it gives that explainability and is trustworthy in our use case. And RAG is only as good as the information that we have in that data source. So it will only answer the question if it's available in our knowledge library. If the answer isn't there, it'll say, I don't know, instead of generating some random response. So this has been a really very exciting opportunity for BHP. On this, we are working with AWS and Accenture to purposefully apply generative AI to the exploration industry and unlock some of the significant challenges our industry faces, especially around access to information sitting in our data. We're facing an increasingly complex challenge to predict and detect mineral systems deep undercover. As we saw, the industry's rate of discovery is declining, and the number of discoveries of sufficient quality to ensure they convert to economically operating mines is also decreasing. Directly linked to this is our ability to enable efficient and accurate access to the huge data sources available to the industry, which is not where it needs to be to unlock the critical information required to solve this challenge. Access to information and data will be a critical enabler to future exploration success. Currently, the volume, variability, legacy, and format of all the exploration data significantly hinders our ability to rapidly interpret insights from it and drive the quality decision making needed at speed to accelerate the rate of discovery of high quality deposits. The application of AI has the capability to unlock material latent knowledge that's stranded in decades of data produced by the industry that's available, but it's not readily accessible or usable. So there are 4 key areas where we believe advances in AI applied to exploration will provide significant value. Turning weeks or months of predominantly manual work into minutes or seconds of data gathering, synthesis, and insight generation will transform our ability to establish more robust predictions. The successful application of AI will transform us as geoscientists from data gatherers and cleaners and massagers to true knowledge workers, accelerating the search and improving the quality of critical exploration decisions. And the ability of this technology to unlock unstructured legacy data for the industry and for BHP, because we perhaps have one of the larger legacy databases in the world, is essential because much of the knowledge and insight is sitting in text and not in our databases. Finally, the value proposition of AI will lead to a reduction in the cost of the exploration process, driving high quality decision making and increasing our probability of success. I thought I'd just close with something a little bit different. I have a 15-year-old son, so there's a lot of YouTube at my house. And if you haven't seen Mark Rober, he's an American YouTuber, check him out. He was an engineer at NASA for 9 years, and he worked on the Curiosity rover at JPL. And he was also a product designer for Apple's Special Projects Group. He just recently released this video like a week or 2 ago about his puzzle robot Jigsaw. And Jigsaw is 200 times faster than the best puzzle doing human out there. I don't know how she won that title. As long as you don't include the 3 years it took them to build it. But anyway, I'll close there with Jigsaw. Thanks so much for sharing your time with me today and your coffee. If you would like to educate me further or discuss ways that we can accelerate our data or our AI journey, please do reach out to me on LinkedIn. Thanks so much.
This has been brilliant. I hope you're seeing the sea of emojis coming up the screen from everyone right now. It's there. That was a really, really great session. So thank you so much for taking the time to talk to us.